Alright, so here's the last video for Unit 2, Conductors, Capacitors, and Dielectrics, where we're going to look at dielectrics, okay? So what happens is, what we talked about in the previous video, in the previous section, the capacitors were filled with air, right? And then we created a vacuum with them, okay? And so, um, I mentioned this a couple times in the previous videos, right? So the capacitors that we talked about before just simply had air between them. And so now what we're going to do is we're going to add dielectrics, okay? So a dielectric, and I forgot the word a, so a dielectric is simply an insulator that is inserted into an electric field, right? And so again, you have these parallel plate capacitors. There's an E field going between them. And so what we're going to do now is we're going to take some sort of insulator and plug it into the in between the plates and replace it, right, with that. We're going to replace the air with this insulator. And this insulator, this is our dielectric. Okay. And so, and the the equations, well, you'll see, will tend to stay the same. We're just going to add one extra factor to it. Okay. So what happens is the capacitance is increased by a factor that we call kappa, right? So it's lowercase kappa, and this is called the dielectric constant. Right, and so it's like, we're inserting this material. We're going to increase the capacitance, and because of that material, okay. So in fact, all the electrostatic equations containing epsilon naught, we can now replace that epsilon naught with kappa epsilon naught. Okay, and really, so for example, to determine the capacitance of a parallel plate capacitor with a dielectric, we're going to do kappa epsilon naught A over D. The kappa for air is 1. And so like if I were to replace so that means the capacitance for air was our equation, epsilon naught A D, which means our capacitance with a dielectric, right, is simply kappa times the capacitance with air, okay? And so the presence of a dielectric, okay, the presence of a dielectric will decrease the electric field because there's an induced electric field, okay? And what we're going to do here is really look at how does this affect, right, everything, okay? And so here's the first thing. We got a parallel plate capacitor whose capacitance C is 13.5 picofarads charged by a battery to a potential difference of 12.5 volts between the plates. The charging battery is now disconnected, and a porcelain slab with a kappa of 6.50 is slipped between the plates. What is the potential energy of the capacitor before the slab is inserted, and what is the potential energy of the capacitor slab device after the slab is inserted? Okay. And so we're going to say U is equal to 1/2 CV squared. And this is before we insert the porcelain. So we're going to say 1/2 times 13.5 times 10 to the pico is 12th times 12.5 squared. And so we get 1.05 times 10 to the negative ninth joules. Okay. All right. So there is our potential energy before. Now, it may just be like, okay, all I have to do is now do kappa times C to find the new capacitance, right? And then I can plug that in. You do have to be careful because once you change the capacitor, the voltage is going to change as well. Okay, so if you want to make this kind of like multi steps, you would need to find the new voltage with the new capacitance and everything. But my recommendation is to do this. Okay, know that the potential energy is simply Q squared over 2C. Okay, so that's plugging in, doing a little bit of algebra, right? And so what does that mean? That means if I want to do my capacitance with a dielectric, I've got Q squared over 2 kappa C air, right? But Q squared over 2C air is this number right here, right? And so what this really means is just going to be my potential over my kappa. And so all I have to do is just simply do U, right? Say U final. We'll call this one U initial. So my final potential energy will be my initial potential energy over my kappa of the porcelain. So that's going to be 1.05 times 10 to the negative ninth divided by 6.50. And so that's going to end up being 1.62 times 10 to the negative 10th joules. Okay. So you could see that once you put that dielectric in, you've decreased the amount of potential energy. Okay. All right. So here's the last problem for the dielectric section. Right. Dielectric is just a quick little, short little problem. So an isolated parallel plate capacitor of capacitance C with vacuum stores a charge Q. A slab of dielectric of mass M near the plates is pulled into the capacitor and enters the space with negligible friction. What maximum speed can the slab reach within the capacitor? So this is kind of interesting because here we're really looking at, right, a speed. So how do we make that connection? Well, if you remember, work energy theorem says work equals change in kinetic energy, but it also remembers like change in kinetic equals change in potential, right? And so this is kind of like the relationship we're going to look at, right? So the change in kinetic energy is equal to the change in potential energy. So delta K equals delta U, right? And we know that U is going to be 1/2 CV squared, okay? But it also equals Q squared over 2 kappa C, right? I'm just trying to give you different ways that you can kind of set all this up, right? And so I would probably use the outer relationships here because we have Q, we have C. Notice that this equation doesn't have Q in it, okay? We have a mass, and so really we're going to just now solve this for V. So V is going to equal, so essentially the 1/2s cancel out. I'm going to end up with the square root of Q squared over kappa Cm, right? And so simply enough, there's my speed, right? And so if I know how much charge there is, I know what the kappa is, I know what the capacitor is, and then I know what the mass is. And so this is the mass of the dielectric, right? This is the kappa of the dielectric. But again, this will be the capacitance in air, right? And this is the amount of charge. And so what happens is, right, based on all that, this slab can move in or out based on what's happening, right? Based on the E field and the amount of charge. Because remember, one will be plus Q, one will be minus Q. Okay. All right. So that ends unit 2 of conductors, capacitors, dielectrics, and we'll get started with unit 3, which will be circuits.